You know, we all learn about gravity in school, right? An apple falls from a tree, the planets go around the sun. But what if I told you that whole story of gravity being a force that pulls things together is only half the picture? Let's get into it, because the real story of gravity is so much weirder and honestly, way more beautiful than you might imagine.
For over 200 years, pretty much all of physics was built on this one idea. Gravity is a force, an invisible pull between two objects. But then, a completely different idea showed up. What if gravity isn't a force at all? What if it's the shape of the universe itself? This one shift, from force to geometry, completely blew up our understanding of the entire cosmos.
Now, to really appreciate this revolution, we have to start with the man who basically built the foundation for all of modern physics, Isaac Newton. His law of universal gravitation back in 1687 was just one of the most incredible achievements in the history of human thought.
And for good reason. Newton's law was just insanely powerful. It perfectly explained why planets move in these elegant orbits, why things fall to the ground, and it even nailed the reason for the ocean's tides. For more than 200 years, it really seemed like Newton had solved gravity, period. It was the absolute bedrock of physics.
But you know how it is in science. As our tools get better and our measurements get more and more precise, you start to see things you couldn't see before. And tiny little cracks began to appear in Newton's perfect foundation. These small, nagging problems that just wouldn't go away. And they hinted that his brilliant law wasn't the final word after all.
And these clues were really specific. First off, for Newton's theory to work, gravity had to be instantaneous. You move the sun, and the Earth should feel the pull at that exact moment. But we already knew light had a speed limit, and nothing could travel faster. Then there was Mercury. Its orbit had this tiny, extra little wobble that the math just could not account for. But the real nail in the coffin? Newton's gravity was completely incompatible with the wild new ideas about relativity that were starting to shake up physics. Something had to give.
And then, along comes Albert Einstein. In 1915, he drops his general theory of relativity. And it didn't just tweak Newton's ideas, it completely bulldozed them and started over with a truly breathtaking new concept about the very fabric of reality itself.
This quote right here, it just perfectly sums up Einstein's incredible idea. He proposed that gravity isn't a force. No, not at all. Instead, massive objects like our sun don't pull on the Earth with some invisible rope. What they do is actually warp and curve the very fabric of the universe, this four-dimensional thing he called spacetime. And it's that curvature that we feel and experience as gravity.
So, hold on. If there's no force pulling us down, then why does an apple fall from a tree? And if there's no force pulling the Earth, why on earth does it keep orbiting the sun? This meant we needed a whole new set of rules for how things get around in the cosmos.
Einstein's whole journey started with this amazing thought experiment, the equivalence principle. Just imagine you're in a sealed elevator, no windows, floating in deep space. If that elevator starts accelerating upwards, what happens? You feel pressed to the floor, just like you would on Earth. There's no experiment you could do inside that box to tell the difference between acceleration and gravity. And that was the key insight. Maybe they're two sides of the same coin. Maybe what we call falling is just moving in the most natural way possible through a curved environment.
Okay, so this is the big one, isn't it? If the sun isn't pulling on the Earth, why are we stuck in this loop, going around and around it year after year? What's keeping us here?
The answer is a concept with a kind of fancy name, a geodesic. But the idea is actually super simple. In flat, empty space, the shortest, straightest path between 2 points is a straight line. We all know that. But what about on a curved surface, like the curved spacetime around the sun? Well, the straightest possible path you can take is now curve. That path, that's a geodesic.
And this just reframes everything so brilliantly. That apple isn't being pulled down, it's just following its geodesic, its straightest possible path, through the space-time that's been curved by the Earth's mass. And the Earth, it's not being yanked around by the sun, it's just cruising along its own geodesic, its version of a straight line, through that huge valley in space-time that the sun creates.
All right, here it is, the Einstein field equations. Now, I know, this looks terrifying, but don't click away, I promise you. The story this equation tells is actually incredibly simple and really, really elegant. Let's just break it down.
See? It's way simpler than it looks. Think of it like this.
On the left side of the equation, you've got geometry. That part describes the shape, the curvature of spacetime. And on the right side, you've got all the stuff in the universe, all the matter, the energy, everything. The equal sign in the middle just says that the stuff on the right tells the geometry on the left how to curve. It's a perfect mathematical sentence for that quote we saw earlier.
Okay, so once you accept this new geometric view of gravity, it leads to some truly bizarre, mind-bending predictions. Consequences that Newton's theory never could have dreamed of, but they've all turned out to be true.
First up is one of the weirdest ideas in all of physics, and that is the idea that gravity can actually warp and slow down time itself.
That's right. Time literally runs slower the closer you are to a massive object. A clock on the ground floor of a skyscraper will tick just a tiny fraction of a second slower than a clock on the top floor. And this isn't science fiction. We've measured it with hyper-accurate atomic clocks. And why should you care? Well, without constantly correcting for this time dilation, the GPS on your phone would be off by miles every single day. It's a real-world effect.
Next, Einstein figured that if gravity is just the curvature of space-time, then it should affect everything that travels through space-time, even something that has no mass at all, like a beam of light.
And just like everything else, light has to follow a geodesic. So as a ray of light from a distant star flies past something massive like another star or a whole galaxy, its path gets bent by that curved spacetime. Astronomers see this all the time. They call it gravitational lensing, and it's amazing. It acts like a giant natural telescope in space, letting us see things that are billions of light years away.
But maybe the most dramatic prediction of all was that huge accelerating objects, like, say, two black holes spiraling into each other, should create actual ripples in the fabric of space-time itself.
These are gravitational waves. They are literally ripples in reality, stretching and squeezing the universe as they pass through. For 100 years, they were just a prediction on paper. But then, in 2015, the LIGO Observatory detected them for the very first time, hearing the chirp of two black holes colliding over 1 billion light-years away. It was one of the greatest scientific achievements of our time.
So, we've gone on quite a journey here, haven't we? We started with gravity as a simple force and ended up with it as the dynamic, curving geometry of the universe itself. It's just a monumental shift in how we see everything.
Let's just look at this side by side. It's not that Newton was wrong. His view was an incredible approximation that still works perfectly for launching rockets and building bridges. But Einstein showed us a deeper, more fundamental truth, that gravity travels at the speed of light, and it plays out on a dynamic stage called space-time, a stage that is constantly being shaped by the actors on it.
But the story, it's not over. It never is. Einstein's theory is a masterpiece for describing the universe on the largest scales, planets, stars, galaxies. But we also have quantum mechanics, which is our masterpiece for describing the universe on the tiniest scales. The problem? Right now, the two theories just don't play nice with each other. They don't work together. So the question that drives physics today is, what happens when gravity meets the quantum world? What really happens inside a black hole? Or at the instant of the Big Bang? Finding a theory of quantum gravity? Well, that's the next great mystery.